It's Amy Both's 7th video, and this is a really exciting one for me because when I first threw this slide together I've just noticed that you can't even see that slide. That's really embarrassing. Why didn't we check that before? Let me just quickly try and fix that. Sorry. There we go. Right, yeah, when I first threw this slide together about fermenting tasty, nutritious, sustainable protein, ideally from nothing more than sunlight and air, what I was really thinking about was an existing process that a number of startups have been developing using hydrogen oxidizing bacteria. Now, last Wednesday afternoon, I grabbed this image to illustrate hydrogen oxidizing bacteria and was blown away by these two images. I'll explain what rocked my world shortly, but first let me introduce the author of the paper that Google took both of these images from, Narcís Rodriguez.
Hello, good evening.
Hi.
Very good.
So yeah, Narcís has been working on hydrogen I'm going to say this wrong every time. Hydrogen oxidizing bacteria at the University of Girona since I think the start of lockdown. Is that correct? COVID?
Exactly. We started to work with it during the lockdown. We had a lot of free time and we started to read about microbial protein, and for us was super exciting, and we decided to move to this field.
Brilliant. So yeah, how are you doing this evening? Is it all going well for you today?
Yes, perfect. We have been working in this topic today also, and I hope we can provide better results in the future.
Brilliant. So whereabouts are you exactly?
Yeah, in my case, we are working in Girona. It's a little city nearby Barcelona, about 90 kilometers from it.
Okay.
It's a city that it's a water hub in terms of research. So we develop a lot of technology relating to water, and we think that microbial protein could very well fit inside.
That's brilliant. Brilliant news for me anyway. I'm a water engineer too. So yeah, what's the weather like for you tonight?
Yeah, here it's very dry. We are in a drought since the last more or less 3 years.
3 years.
And
wow.
yeah, so in our region we are starting to get in very big trouble, I would say.
Oh dear, sorry to hear that. So yeah, are you able to see the live stream chat?
Yes, I am.
Cool. So I think Gerrit's just said, is it just him or is the audio really soft tonight? Laura, what are you thinking? Is it the same as last time or? We'll try. I should keep speaking because there's no point in me saying something and then. Gerrit, does that sound better to you? Anyway, there's about a 20-second lag on this, so we'll hopefully find out soon from Gerrit if the audio is now okay for him. We did get a new audio desk, so this is the first time it's been tried out, so it might be something to do with that. Anyway, yeah, if you could keep your eyes on that in case I miss any questions that are coming in, that'd be brilliant.
Okay.
And yeah, speaking of the live chat, I'd like to announce the winners of our quote competition. So the concept was that you invite a friend to quote you in the live stream chat, and the winning pair would each win their choice of an Adafruit spectrometer, a bag of bits that'll help you if you'd like to build an open flexure microscope, a Raspberry Pi 02W, or an hour's free consultation with me. And I don't know if it's this last one that's putting everyone off, but while I would like to announce the winners, I went through all the live stream this morning and I couldn't find a single quote, basically. So please let me know in the chat or in the comments if you're watching this in the replay why you think nobody wants to play. There have been plenty brilliant comments in general in the chat, so maybe everyone's just holding out for the big prizes. If this is your first Amiable video, I want to feature a trailer to each week's live stream on our front page, but that feature only works if you've got over 1,000 YouTube subscribers. So when we hit 100,001, the best live stream comment wins their choice of either a Pioreactor or an open flexure microscope. Anyway, please do say hello in the chat if if you're watching live, or in the comments if you're viewing on demand. And please also add any questions or comments that you have as we go through. Anyway, before we get to the exciting bit, let me give Narcís a quick recap of what we've been doing, and then I can update everyone on the spirulina culture. So we started with some spirulina from Dina on Etsy, which I put in a Pioreactor, and the Pioreactor stirred it and illuminated it with a pair of white LEDs, measured and maintained its temperature at 32.5 degrees C, and measured its optical density. So it grew really well, as you can see here. So we took a 100 microliter sample of it and inoculated 10 milliliters of fresh culture media, also from Dina Etsy, with that sample. And it didn't do so well initially, but eventually it started to grow. Then I installed the Adafruit spectrometer to measure colour, and I topped it up to 15 mil with fresh media so that the spectrometer could see it and reduced the light intensity. But it started dying. So I replaced 5 mils of culture with, replaced 5 mils of that culture with a much thicker culture that had been growing in the beaker, and it kept dying. So our main discovery was that basically the high LED that we were getting previously, high LED intensity of about 50%, was responsible for the early growth, and when we dropped to 5% and lower, we weren't getting that growth. But before realizing this, I inoculated 10 milliliters of fresh culture media with 5 milliliters of our beaker culture, and it continued to die until the light bulb moment, and then I increased the LED intensity to 50%, and it took off. It then predictably died again when I forgot to turn the LEDs off after last week's live stream, but it recovered when I restarted the diurnal LEDs. So you're seeing it going up. It goes down over its night period and then increases again during the day. So in this story so far, we've been doing everything in batch mode. So that means that the reactor contains a single batch of nutrients from the start, and that's all it's getting, with the exception of the light and the air. And last week we added a 50 ml centrifuge tube and filled it with culture media, and then hooked up a peristaltic pump. That would mean that we could operate in fed batch mode, adding nutrients at appropriate times. But we also added an empty tube and a second peristaltic so that we can hopefully avoid overflow, harvesting the culture while replenishing the nutrients. This is working in chemically static or chemostat mode. But better still, and what we've set up, is using the optical density measurement. The Pioreactor can then keep the turbidity, or the concentration of the cells, approximately constant. So that's what we've been doing. So let's have a look at how that's going. So first off, let's see. This is the system. So I did a bit of filing here, and it now fits perfectly. And that's it. You can hopefully see the LEDs flashing there. So that's the two. They're now at 75%, which are flashing. It's currently in a day cycle, and the probability of it actually changing over and running the pumps while we're looking at it is very slim. But anyway, let's have a look at what the Pioreactor is seeing. So here we've got the optical density, which you can see is pretty constant because it's being kept constant. The normalized optical density, you can see a few disasters that we've had. So there was, this one I think was around me having to change an LED because one of the LEDs started flickering and then died. So I changed that over. That seems a little odd, but anyway. And then this big one here, you can also see the massive temperature drop. That is because a fuse went in the lab here, and all the power went out, and it took us a little while to see that had happened. So the temperature dropped. So anyway, but it's currently up and it's growing quite well. So all seems okay there, I think. Right. So. Let's see. Oh, in the questions we've got lots. Okay, are they? I think they're all about the audio. Are they all about the audio? Audio, more volume. Oh, Julianne Holloway at Arizona State University. Okay, cool. Thanks, Morgan. So we'll get in touch with her. And okay, Garrett still wants more volume. She gave a talk at the Taraski Institute on using magnetic fields for tissue engineering. Cool. Excellent. So these images then, so the issue really is when we're talking about hydrogen oxidizing bacteria, which I think are the ones that are being touted as the best tasting ones. The issue with the hydrogen oxidizing bacteria, or HOB as I might just start calling it, is that it needs hydrogen. And hydrogen is rather explosive, and the risk from people eating the microbes and the metabolites that we produce is probably high enough without us adding the risk of blowing them up. So, Narcís, how did you overcome that risk?
It was a good strategy to, instead of having like a bottle full of pressurized hydrogen, instead of that, what we are doing is to produce the hydrogen inside the fermenter. In this manner, the hydrogen is produced at a constant velocity, and the microbes are directly uptaking this hydrogen. So in this manner, it is very difficult to get very high concentrations of hydrogen because the bacteria will tend to consume it. In any case, if, for example, bacteria died for any reason, since we have both the anode and the cathode inside the same reactor, any excess of hydrogen would be consumed by the anode itself. So it's a kind of a cell control.
Okay, cool. So, I'm just wondering, do you know what happens when that happens? So you're adding energy to the system. It's creating hydrogen and oxygen.
Exactly.
Where's the energy going if it's just cancelling itself out at the electrodes? Does it heat up or?
No, basically, imagine in a moment where, imagine that we don't have any bacteria inside our fermenter. In that case, we would, at moment zero, we would start producing hydrogen in the cathode, oxygen in the anode. But over time, the presence of oxygen would start to colonize the cathode. And thermodynamically, it's much easier to reduce oxygen than to produce hydrogen.
Okay.
So basically what would happen is that you will basically produce oxygen and hydrogen would be not produced at all.
Okay, right. Cool. So yeah, I'm very tempted to leap in and ask you all my questions about your papers and work, but I'm gonna resist that because you also very kindly agreed to join us for our first journal club. So to avoid too many spoilers for people who are going to read the paper, still to read the paper, I'm going to resist there. If everyone's happy, we'll then share highlights of that meeting, hopefully in the next live stream. But there is one thing that I wanted to ask you. You mentioned at the start that, like me, you're in water. You're a water engineer, or how would you describe yourself?
Yeah.
Water engineer.
Yeah, I have a doctorate on water engineering.
Right, cool. So, same as me then, pretty much, although water's obviously a big field. But why did you start researching hydrogen oxidizing bacteria?
So basically, the work that we were doing before the COVID lockdown was trying to treat nitrogen in water using electrochemistry.
Okay.
And
so that's like nitrates.
Yeah, basically nitrates in groundwater. And we were using some specific kind of bacteria that can use the electrodes to remove this nitrate. And then we realized that, in fact, the problem of nitrate pollution in groundwater comes from the way we are producing food. Now we are consuming a lot of animals and plants, and we are doing it in a also in a very inefficient way. We are, for example, in the agriculture, there is an excess of fertilization that is coming directly to groundwater and contaminating it. In part, this is a failure of the way we are fertilizing, but there is a second part, a second story, which is that plants and animals are not very efficient on consuming nutrients and producing a product, a protein. And taking everything together and reading in the literature, we realized that on the one hand, we could produce microbial protein that has a very high efficiency on converting the nutrients into an edible product. Because, for example, imagine that you want to eat an orange. You are cultivating a whole tree and you will just eat the orange. The rest is lost, is nutrients that we are consuming and we are not using it then at the end for food. So on the one hand, we realized that these microbes has a very high efficiency on consuming nutrients, and on the other hand, we were experts on electrochemistry, and we mixed everything together, and we say, okay, we could, in a way, produce food out of electricity and carbon dioxide and ammonium. This is perfect for us, and we started to work on this.
Brilliant, cool, excellent. So, looking at the chat, Cam is saying that those normalized OD drops look pretty okay in his opinion. No, it's about a 3% drop. Just looks large due to the chart scale. Yeah, brilliant. Okay, so yeah, sadly I only have one Pioreactor at the moment, and I don't have any hydrogen oxidizing bacteria to start an experiment with anyway. But I have started to collect the bits that I'm gonna need. Let's bring this up. I'm gonna move, and Cam will be probably annoyed that I keep moving this thing around. It's not the best of ideas, but anyway, this arrived in the post today. It was supposed to arrive yesterday, so I should have had time, but this is just proving this is extremely live. I have basically turned it on once before. I have read the entirety of the manual because this was so cheap that it came with a single A4 sheet for a manual. It does have a number of upsides over many others that I looked at. It's linear, I understand, which I think is a good thing. So instead of it switching, it's quite hefty, and it's got a transformer and a heatsink. It's also the smaller one, so it's just got a heatsink instead of a fan, which is good for me for a couple of reasons. One, I can put it on its back like that so people can see what we're doing, and two, it's not going to be too noisy for the microphones. So I understand that right, I need to plug these in first, and I need to attach it to so you mentioned that you're experts in electrolysis, so try and let me know before I do anything too dangerous. It only goes to 15 volts and 2 amps, so I'm hoping I won't kill myself. I'll peel these off so that we get a better view. And right, as you saw when we started, I made such a mess of it. I got this platinum, so it's that 5 micron platinum coating anode, and we're now thinking, so titanium was mentioned, and we're thinking it's perhaps on a solid titanium backing or something. It was only like £9, so I'm amazed. But basically these snips they've got dents in them now instead of cutting through. I got a big pair there that couldn't get through it either. I managed to get through a little bit with a Leatherman, but then I couldn't get beyond the first bit. So I'm going to figure out a better way of cutting this up. But in the meantime, we've got... Right, so just 5 minutes before we started, we managed to find these 2 bolts, because I've lost them now, but the bolts I bought were too big. So hopefully these, I don't know, they're both carbon steel. Is that okay? For
the cathode, it's okay.
Right.
any conductive material made of stainless steel, graphite, etc. Anyone can be used as a cathode, and they can produce hydrogen.
Okay.
But as the anode, the material has to be some very specific materials, because otherwise they don't produce oxygen and they oxidize themselves. So,
okay.
So ideally, the anode should be like titanium coated by platinum, tantalum, or other metals like that.
Right.
In the case we use
stainless
steel,
should be okay for what we want to do.
Exactly.
Once
this is
I can
perfect
cut it.
as the anode. Yeah.
Right. And yeah, platinum, titanium, and less than £10. So brilliant. Right, but hopefully, so what I'm just going to take some tap water for now, and I'm going to put it in here. And then we'll see if anything happens, right? I'm hoping on one side at least I'll get some bubbles, right? I should get some hydrogen at least.
At least some hydrogen.
Yeah, okay, cool. As long as I don't have them touching. They're currently touching. That's not very good. Come on. Why have they decided that they're going to touch now? There we go. Right. They're touching again. There. Right. Okay. I'm going to stop fiddling. Right. So I'm going to connect. I guess it doesn't matter which I connect to which, I guess, because I've got the wrong metal.
But
anyway.
in the case it was the right metal, the black is the cathode. So it should go to a stainless steel.
Stainless steel.
And the red should go to the titanium and platinum, because it's the anode.
Platinum. Yeah. Okay. So the manual said that I hook it all up and then I turn it on and I adjust the voltage first. What voltage should we?
Usually these machines can control or voltage or current. So now you see the light is in the current mode. So now you can control only current.
Okay, so I just turn up the current.
And now you have seen that it has moved to voltage. It means that now you can increase the voltage.
Oh, okay. Okay, nothing's happening so far.
Yeah, probably they are touching themselves.
I don't think they are.
Maybe the water that doesn't have enough conductivity.
Shall I crank it all the way up?
Yeah, you can increase more. When something happens, you will see that the current starts to grow.
$20 milliamps. Oh,
Now, basically what would happen first
starting to look a little bit different.
First, what will happen is that the oxygen that is present in the water will start to be reduced, and after that you can start producing hydrogen.
Okay. Should I turn up this one as well? Or will that?
No, you cannot modify it. Yeah.
Oh, okay. Yeah, we're starting to get bubbles. Can people see that? Right, focus. So, the hydrogen electrode is indeed producing something. And we've got lots of comments. Cam thinks this is wild. Laura's looking scary. And Cam, what are those things? I've got a very small screen. I can't work out what the four things that Cam's sent us are. But we're getting some bubbles there.
Yeah, and then if the anode was titanium coated by platinum, you would also see bubbles. Now, in principle, we shouldn't see anything. Only at some point, the electrodes should start to oxidize themselves.
Cool. Right, should I try and ignite this? I'm pretty sure it's not enough to be dangerous. I'm guessing. I've got a little hole at this side, so I'm gonna... It's not making a pop or anything. I wonder, should we increase the conductivity?
With increased conductivity, you will have more production with a lower quantity of volts.
Okay.
Basically, in electrochemistry, we are moving electrons from the anode to the cathode. This is a negative charge. And we need to move a positive charge from the anode to the cathode. And conductivity helps this process. It accelerates the velocity of this movement.
So I'll do I turn down the voltage? Right, that's all 0. So I'll turn that off. I'm going to disconnect these. And right, let's say we were going to put it into the so I mean, stupidly I didn't bring any salt, but if we were going to put this into our spirulina, we would be using this stuff. So I'll maybe put some of this in. I'm pretty sure it's going to contain some sodium chloride as well as other stuff.
Yes, when I say conductivity, it means any salt. But are usually the salts that you need to cultivate any microorganism. So in tap water, there is the amount of nutrients is super low, so we wouldn't be able to cultivate anything.
I wonder if I can get a pop with that. Oh, not if I've turned this off. Why is this not working? Nah. Right. Let's put a bit of this in. I've got another... I've got a cap. So like, yeah, 5 minutes before the video started, I was drilling these holes, and they came out too wide. So, right, this. Oh, the Pioreactor's. Sorry, it was too late. The Pioreactor has just decided that it's high enough optical density. You might have heard the motors spinning there. Garrett, I'm going to try turning up this here a bit and seeing if you're happy with that now. Does that sound any better for you? Oh. I'm going to bring this so it's... Try and bring it so it's just in shot, just in case it does another set. Or was that the third? So basically what it's doing in turbidimeter mode, I've set it up to cycle 0.1 mils. So it takes, first of all, it adds 0.1 mils, and then it removes 0.1 mils, and then it removes another 0.2 mils just to ensure, because it's constant level, so it's going to the level of the outlet pipe tube. Right, okay, so I've got that in there. I'm going to reconnect. This was my cathode. This is my anode. Right. Now I'll put those where you can see them. I'll turn this on. Increase the voltage. Oh yeah.
Yeah, you see that the current rapidly increases.
Yeah.
And the production of hydrogen is much higher, no?
Much higher. And I think I'm seeing some stuff coming off the anode as well.
Yes, the
You've
anode
seen?
is, since it's stainless steel, it will oxidize
Right. Okay.
itself.
This
So
isn't even
it's
stainless steel. I think it's just carbon steel I'm using. But
mhm,
the bolts that I bought that were too big, they were stainless steel. Right.
mhm.
Can I get a pop now? I'll try lifting the lid. Oh, have I just been shorting the... I'm hearing clicking, which I presume is me short-circuiting or something. No. Oh, there was one. Did anyone see that?
Not really, I guess.
I've got it. I'm hoping you saw
Oh,
that.
yes.
Yeah,
Mm.
go. So yeah, what we've got here, I'm guessing I had sort of bigger flash there, is what they call in YouTube at least hydrogen HHO. So it's just a mixture of hydrogen and oxygen gas, which will give a little pop like that. Right, and yeah, you can see this is now a green mess of stuff. So
yeah, this is because the anode. That's why it's important.
Yeah, I'll turn that off for now. And then, yeah, what do you think? Other than just my general ineptitude in managing to buy all the wrong stuff and all the wrong tools and so on, what is going to be our biggest difficulty when we try to do this?
In my opinion, or at least the difficulty that we are finding, it's that the amount of hydrogen and oxygen that is produced by electrolysis is not the same than the one that is required by bacteria. So hydrogen oxidizing bacteria requires less oxygen than the oxygen we are producing in the system.
Okay.
So from time to time we need to flush out this excess of oxygen, and from our understanding, this is the main limitation we are trying to face now.
So how do you flush out the oxygen then?
In our case, we do it by carbon dioxide.
Okay.
We use a pressurized carbon dioxide, which it's something that it can seem strange, but it's a material that can be bought in aquaria shops, for example. The people that has aquaria,
yeah, and soda streams
at
as
home,
well.
They use it for cultivating plants inside their aquariums. And so to have like pure carbon dioxide is commercial.
Okay, right. So it should be reasonably easy for us to get hold of that. I was planning on passing air through it, so air will contain carbon dioxide. Is that not going to work?
No, because air also contains a lot of oxygen.
Yeah.
So at the end, you will introduce more oxygen to the system also.
Right. Okay. So, yeah, everyone, please do chuck in any suggestions for what we could do here, how we could fix this. One thing I'm thinking of is that normally, so the little experiment that we've just done here, the HHO gas is kind of not particularly useful. Hydrogen's generally what people want to produce, so they tend to put a membrane or something between the two,
Exactly.
or they have two separate reactors so that the bubbles are rising. Could we do that?
This is another way that you have an electrolyzer where you produce hydrogen in one side, oxygen in the other side, separated by a membrane, and then you introduce all the hydrogen in the fermenter and only a portion of the oxygen in the fermenter. This is a second option that could be tried. So in our case, we are working always with the electrodes inside the reactor to avoid the possible inefficiencies that this can produce. But of course, we are working at a more thinking in a larger scale levels, no? Where we are able to control easily the oxygen concentration inside the reactor, for example.
Yeah. Okay. So, are there any other disadvantages to that?
We are exploring them, but we still haven't found them.
I think So I did in our sort of practice yesterday. Not that practiced any of the. In fact, we practiced virtually nothing other than just ensuring that we had a good chat. Anyway, you were suggesting that pH might be an issue if we were to use a membrane.
This can be an issue in the electrolyzer, basically. So in the anode, basically we are producing electrons and we are also producing protons. And in the cathode, we are consuming electrons and consuming protons. If the two electrodes are in the same media, the pH will remain neutral because the electrons consume it, the protons consume it at the anode. The protons produced at the anode will be consumed at the cathode. But if you put a membrane in between, what will happen is that all the protons that are produced in the anode will not be transferred to the cathode. So the anode will get acidic and the cathode it will get basic.
Right. And another thing that we discussed was perhaps using other things that are going to consume the oxygen. So bacteria that would consume it.
Yeah, any bacteria that could be like an oxygen scavenger would be perfect to balance these stoichiometries.
So for that, we just need to add a carbon source. Is that right? If we have a mixed.
Yeah, the easy way would be to add a portion of carbon source, and then you would have a co-culture of hydrogen oxidizing bacteria and another organotrophic bacteria.
Cool. Okay. Well, lots of things to work on, I guess. I suppose, yeah, the carbon dioxide, like you've been doing, is probably the easiest way to start. And the nice thing about carbon dioxide is it's I think it's kind of not inherently safe, but our bodies are used to detecting carbon dioxide and knowing when there's a problem. So it's not like other gases that you can easily asphyxiate from, because we have basically loads of carbon dioxide sensors that tell us that we need to breathe again. So yeah, that's cool. Gerrit's asking, would that power supply be sensitive enough to generate the right amount of hydrogen for HOB in a 20 ml vessel?
Definitely, yes. Now, for example, we got a second paper, and we were working in a 1 liter reactor, and we were applying a current of maximum 200 milliamperes. So
I think his concern
in a 20 ml by this power source, you can provide a lot of oxygen, a lot of hydrogen. Sorry.
So I think his concern is that let's see, can I turn this on? Oh, we can turn that on safely. That we can only go to, what is that, 10 milliamps? And the manual says that that's basically 1% plus one digit. So basically, if we've got that saying 10, it might be actually 20 or 30. Is that going to be too high for a 20 milliamp? Oh, sorry. In fact, no, I'm on the right one. Good. Thank you.
it's an option to explore, no?
Yeah.
Because we got until this 200 milliamperes, but we know that we could explore higher values.
Yeah.
In this system. Then, as far as I know, a power supply that can work at this sensitivity has a price. Power supply with a higher sensitivity has a higher price. So
yeah, so this was £25, and it was basically about 10 times the price if I wanted a linear. I don't know if we need linear. What I did want, however, was one that doesn't have a fan, and I found ones without fans with 3 digits. But yeah, they were much more expensive, and I can't remember, there was another issue. Well, they weren't going to arrive in time. That was certainly an issue. But anyway, my hope is that I can run with this one. Gerrit, perhaps you could get a more accurate one if you're willing, and we can work out. But what we'd really like to do, if we could, so I've been discussing this with Cam a little, is if we could actually use the pulse width modulation PWM outputs from the Pioreactor to run that. So you've got 5 volts there. I haven't a clue how current control would work there, but if we could get that so that we didn't need all this stuff and we could just do everything in the Pioreactor, that would be brilliant, I think. Cool. So I think we should leave it there for now. Yeah, if you fancy discussing Narcís's work, Gerrit, who has the concerns over power supply, and Narcís will probably be grilling you when we do this again on that. Yeah, he's arranging a journal club, so that's in the forum. So if you head to forum.amybo.org and let him know your availability, or just follow the discussion there so we can all meet up online. I'm hoping it's going to be next Monday evening, if enough people can do that. And then I hope to be back here next Wednesday, possibly with some highlights from that first journal club meeting, and an update on both spirulina and how we're progressing with hydrogen oxidizing bacteria. So yeah, thank you very much, Narcís. Thanks for joining us again, and thank all of you for watching and getting involved. Thanks for all the comments. Thanks, Morgan, for the very cool. It's cool. And yeah, together, let's fix this nitrate pollution issue, as well as world hunger and the climate crisis. Why not? So I'll catch you in the next one. Bye.
Thank you. Bye.
Thanks. Ah, thank you.